Okay, so I want to keep moving along a bit. So Rho and Vega, they're a little bit easier, so I tried to cram them into one lesson. So Rho is the rate of change of the value of a portfolio with respect to the risk-free interest rate R. And so again, our portfolio that we're considering for right now just has a single asset in it, which is a call option. So this will be the pricing formula for my portfolio. And I want to take the derivative of that with respect to R, the partial derivative with respect to the risk-free interest rate. So what's going to happen here, the first term will be relatively easy. So I'm going to use, again, the linearity property. So derivative of a sum is the sum of the derivatives. This SE to the minus Q t minus t, this doesn't depend on R, so I can move that across the derivative operator. So the derivative of the first term is going to be SQ t minus t. Hold on. There. SE to the Q minus Q t minus t times the partial derivative with respect to R of capital phi of d plus. And then I need to subtract and now here I'm going to take the product rule because k e to the minus r t minus t and phi of d minus, those are two functions that both depend on r. So by the product rule, it's going to be the derivative of the first function times the second function plus the derivative of the second function times the first function. So the derivative of the first function with respect to r is going to be k times minus t minus little t. So this is going to get a bit complicated. I probably should have used a substitution to get this. But this minus sign here came from this minus sign here. Then when I take the derivative, uh-oh, did I make a mistake? So when I take the derivative of k e to the minus r t minus t, so r is the variable I'm taking the derivative with respect to, and that's multiplied by minus capital T minus little t. Yeah, do I have the minus? Oh, I switched the order of the term, so it is okay. It is okay. Right. Okay. Yeah. Right. Well, there's going to be two minus signs because so this is the mistake, is that when you take the derivative with respect to little t is minus in here, and the r. So minus. Oh, sorry. I'm confusing myself. I'm taking the derivative with respect to r. I got ahead of myself. I was working very hard right before class on the theta, which is the next lesson, where I'll be taking the derivative with respect to little t. Yeah, so okay, so this is correct. So I have minus capital T minus little t times k. So that's why I get a minus capital T times minus little t times k times e to the minus r t minus t times phi of d minus. So it's the derivative of the first function times the second. Then plus the derivative of the second function. So I'm taking the partial derivative of phi of d minus and multiplying that by the first function, k e to the minus r t minus t. Okay. So crisis avoided. And now by the chain rule, so I've kept the this first bit here is going to stay the same, and now I'm trying to take the derivative of a function of d plus with respect to little r, so I have to use the chain rule. And so I'm starting to do a few more steps in each line here. So we've already seen that the derivative of capital phi of d plus with respect to d plus, that's just little phi of d plus. And then by the chain rule, I need to multiply that by the partial derivative of d plus with respect to r. And then the same thing's going to happen in the second term of the part in the square brackets here, where I have to take the derivative of capital phi again with respect to d minus. So I'll get the derivative of capital phi of d minus is just lowercase phi of d minus times the partial derivative of d minus with respect to r. So that's just the chain rule. So I've used it here, and I've used it here.
Sorry, I think I missed something. What were we denoting? What is the little phi denoting?
So that's the derivative of capital phi. So remember, we've defined capital phi as the integral from minus infinity up to z of little phi.
Oh, okay.
Right? Yeah, so little phi is just the derivative of capital phi, essentially. So next thing I'm going to need are the partial derivatives of d plus and d minus with respect to r. So again, this turns out not to be too difficult, because if I look at the definition of d plus or d minus, so I can again look at these at the same time, I can write this as, so I have log of s over k divided by the denominator minus q times t minus t over the denominator plus or minus sigma squared over 2 times t minus t over the denominator. I'm going to take all of those bits that don't depend on r and just lump them up into something that's constant relative to the risk-free interest rate r. And then the only bit that's left over, the part that's going to depend on r, is going to be this plus r divided by the square root of t minus t. And so I'll think of this t minus t, the actual quantity, as just the square root squared. So one of those square roots is going to cancel. So I end up on the top with r times the square root of t minus t. And on the bottom, I just have this sigma left over. And now this is actually a very easy function to take the derivative, because I want to take the derivative of this with respect to r. And so this is just some number times r to the first power. So I can use the power rule to say that's just going to be the square root of t minus t divided by sigma. And again, because it doesn't have the part with this plus or minus sigma squared ended up being constant with respect to r, that's just gone. So it doesn't matter if I'm taking the derivative of d plus or d minus. I'm going to get the same value, square root of t minus t divided by sigma. So if I substitute that in for d plus and d minus, I end up with this expression here. So the first term we already had, and then this is just what we had on the slide before, except the partial derivative with respect to r of d plus or d minus. That's just been replaced with square root of t minus t divided by sigma. And I'm going to rewrite that like this. So it might take a little bit of thinking to get from the top point to the bottom point. The first term stayed the same. And all I did was reintroduce the square root of t minus t in the denominator. So I recovered just a square root of t minus t squared in the numerator. And then I factored that out, and that's where this came from. Then, because I've introduced this s in the denominator here, I can factor out an s over here as well. And so maybe with a little bit of staring at this, you'll convince yourself that I can move from this line here to this line here. And now if you look at the part that's in the square brackets, that's exactly the same expression that we showed was 0 when we were trying to simplify the expression for delta so that I could compute gamma without having to take the derivative of all three terms. So if this thing in the square brackets is equal to 0, then it doesn't matter what s and capital T and little t are. This whole second line here is equal to 0. And so my expression for rho is just going to be k, oops, I'll do it backwards. So k times t minus t times e to the minus r to the, so e to the minus r t minus t times capital phi of d minus. So that's us getting rho. Vega is the rate of change of the value of the portfolio with respect to the volatility sigma. So now I just need to take partial derivatives with respect to sigma. So again, we're going to start off with the Black-Scholes formula for the price of a European call option. And I want to take the derivative with respect to sigma. So that's my definition of Vega. And so this one looks like it should be fairly straightforward, since here, S, E, Q, T, and T, there's no sigma there. And the same for the right-hand term. I have K, R, T, and T. So I'm just going to have to, by the linearity property, this is the derivative of a sum, it's the sum of the derivatives. And I can move these terms that are constant with respect to sigma across the derivative operator. So I can write this in this form here. So I have Vega equals S e to the minus Q T minus T. And then I'm starting to do more operations in each step. So by the chain rule, the derivative with respect to sigma of capital phi is going to be the derivative of capital phi, which I said now is lowercase phi. So once you've sort of proved something one time, or once you've used a result often enough, you don't have to keep proving it every single time that you do it. And then by the chain rule, because I'm taking the derivative of capital phi of d plus is a function of sigma, so I have to use the chain rule. And so to get the correct derivative, I need to multiply lowercase phi of d plus by the derivative, the partial derivative of d plus with respect to sigma. And then I'm going to do exactly the same thing to the right-hand term, except it's just going to be a lowercase phi of d minus, and then by the chain rule, partial derivative of d minus with respect to sigma.
So is because I'd written earlier that Vega was dv d sigma, and we had the, v being the independent variable there.
Yeah.
So is Black-Scholes the formula then, in this case, just one of several different varieties?
Right, so v is just, they chose that letter for value.
Yeah.
And so it's the value of a portfolio.
And Black-Scholes is one way of calculating that, is the idea?
Well, I said in the first slide, the portfolio I want to consider during this session is a portfolio that contains one call option.
Oh, okay.
Okay, so for this, V is in general. So for instance, when you're doing the homework, I asked you to calculate Vega of a put option. So then you would say, V of P, that would be partial of P with respect to sigma. In general, V is just whatever your portfolio is. So you could put, several shares of the asset into it. You could put, some options into it. Yeah. Yeah, so V is kind of the general idea, and then because I'm only pricing a portfolio with a call option, I've just gone to just using the call option pricing formula. Okay. So did I explain all of this slide already? Yes, I did. Okay. So what I need now are partial derivatives of d plus and d minus with respect to sigma. So I'll start out just by writing down what d plus minus is. So again, I'm using this sort of placeholder, so I can do them both at the same time. And so it turns out I can separate this into two things that are going to be easier to work with. So there's one term in the numerator here, this sigma squared over 2 times t minus t that has a sigma squared in it. So I'm going to put that all by itself on the right-hand side. And so what I've ended up doing is taking the sigma squared over 2 divided by sigma. So that's just this sigma here divided by 2. Then I have a t minus t in the numerator and a square root of t minus t in the denominator. So I have t minus t and square root of t minus t here. And then I have to just take what's left and put that in the other term. So I have a log of s over k plus r minus q times t minus t. So that's just this part here, divided by the square root of t minus t. And then I'm going to, because I'm setting myself up to use the power rule, I'm just going to write that as sigma to the minus 1, because I'm for me personally, less likely to make a mistake if I write it this way than if I try and take the derivative just with the sigma in the denominator. So now I'm going to go ahead and take the partial derivative of d plus and minus with respect to sigma. And notice it's going to kind of carry through this time because now I have the plus or minus and there's a sigma here. So when I take the derivative, I'm still going to have this plus or minus thing here. So it's now getting important that we be careful with the plus or minus notation. So it doesn't look like I really did anything, but all that happened here is in the first term, I took minus 1 times this coefficient here. So it's minus 1 times this fraction to the times sigma to the negative 2. So that's just the power rule for the first term. And then the second term is pretty easy. That was just sigma to the 1. So by the power rule, I just get 1 times this quantity here times sigma to the 0, or just the quantity, just the coefficient that was multiplying the sigma in the second term. And so I'm going to try and unsimplify now a little bit to see if that's going to help me, because none of this is looking particularly pretty yet. So sometimes when you put it back together, it will resemble something that you've seen before. So I'll try doing that. So I'm going to multiply the right-hand term by sigma squared over sigma squared, just so that I can have the same denominator for both terms. And so that's going to make this sigma squared over 2 pop up in the numerator again. And so now my notation's getting a little bit tricky, but this turns into minus over plus, which just means now that if I'm talking about d plus, I refer to the minus 1 here, and d minus refers to the plus 1 here. But it's starting to look a little bit more familiar again. So the sign here is changed, and I've picked up a sigma squared in the denominator, but that's an expression for the derivative of d plus or d minus with respect to sigma. And now I need to substitute that into this formula here. And generally when I'm working, I like after every step for things to look like they're getting simpler. And this is clearly going to make it get a lot more complicated. So I put this kind of wisecrack in here. It looks like it's going to get worse before it gets better. And so usually, you can do this, and if you don't make any mistakes, you will get the right answer. But when I see something that gets this complicated, I start thinking like, maybe there's a better way to do this, or it's at least, it's sort of a risk management technique. Now all of a sudden, investing a little bit of time to maybe not have to do this might be a good idea. So let's see what I have down here. So let's look at this. This result's been handy already. So maybe I can squeeze a little bit more mileage out of this. Okay, so more here. So I'm going to rewrite this. So if I add the second term to both sides, I can just put the equal sign in between here. And then since sigma and the square root of t minus t are going to be on both sides, and they're both greater than 0, I'll multiply both sides by that. And then move this s from the denominator of this side just into the numerator on this side, so the fractions will go away. So I can simplify this expression a bit, and I have this. And so does that look like it's going to be helpful? Well, I've got an s e to the minus q t minus t here, and I've got a k e to the minus r t minus t here. So far, things are looking good. And so this was my expression for Vega. So this is exactly what I had on the previous slide here. And if you look at this a bit, I've got this d plus term here, so the derivative of d plus with respect to sigma, and here a derivative of d minus with respect to sigma. And so it turns out I can rewrite this like this, because I have, on the previous slide, I have this equality relationship here. And so now this is starting to look quite a bit better. And now the next big step that I can make, so was that clear? I guess I didn't mention one thing. So what I did to get that, I took the derivative of this expression here with respect to sigma. And that turns out to be exactly what this is. And now I can replace one of these guys with the bit that I have here with the s. And so if I can replace this thing with the first bit here, then I can just factor that out. And so essentially it's that same computation that we've done. It's kind of complicated, but just changing this d minus, this phi of d minus, into a phi of d plus and some other stuff. But since I've already done that calculation, I'm just going to reuse that result. Then I end up with the partial derivative of d plus with respect to sigma minus the partial derivative of d minus with respect to sigma. But that's the same thing, so I can do this linearity property backwards. If I had d plus minus d minus, and I took the partial derivative of that quantity with respect to sigma, I would get exactly this thing here. And now the trick is to remember that d minus is defined in terms of d plus by this relatively simple expression. So if I want to look at d plus minus d minus, so the thing that I'm trying to take the derivative of, I have d plus minus the quantity d plus minus sigma times the square root of t minus t. And so that's d plus minus d plus, so the d plus goes away. And then I have minus negative square root of t minus t. So that's just going to be sigma times the square root of t minus t. And then I'll take the derivative with respect to sigma of both sides of this. And so this is actually pretty straightforward. This is just the power rule now. So the partial derivative of sigma times the square root of t with minus t with respect to sigma is just going to be the square root of t minus t. So that's quite a lot less work than I was looking at before. So now I can plug this in here, and I'm finished. So that's my expression for Vega. So this partial derivative here of d plus minus d minus with respect to sigma, that was just the square root of t minus t. And so then I have this s, t minus t, t minus t, and the rest, e to the minus q t minus t times phi of d plus.